Suppose dy by dx equals x plus y, where y0 equals 1. Use Euler's method with a step size of 0.2 to find an approximate value for y1. Well, basically, Euler's method is a numerical method that's exactly equivalent to following a slope field. So basically, you get the gradient of a point at an initial x and y position, and then you use that gradient, you follow it a little bit along a step length specified, in this case 0.2. So you go that far in the x direction, and the distance you go in the y direction, well, it's the gradient times the step size, and that brings you to a new value. Now, Euler's method is actually, thankfully, in the formula book, but it does need deciphering a bit, because if you just see it like this, and you've never seen it before, you wouldn't have a clue how to do it. So if you look at what's in the formula book, it says yn plus 1 equals yn plus h times f of xn yn. And the xn plus 1 equals xn plus h. So if you think about h, well, that is exactly the same h as we see in differentiation from first principles. So h is your little dx. It's a slight nudge in the x direction. And for Euler's method, it's always constant. In this case, 0.2, the step size, and this step length is written, that is h. So h for this particular question equals 0.2, right? The f of xn yn, that is the gradient function. That is dy by dx. So in our case, the f of xn yn, well, we know dy by dx is x plus y. So our f of xn yn is going to be xn plus yn. Okay, so if I just represent this using a little diagram, so we take a point, and this is going to start at x0, y0, which we know. Here we can see if y0 is 1, well, let's just write that down. x0 is 0, because it tells you when x is 0, y is 1. So that's the point where you start from. So y0 equals 1. So we start from there. Let's say, if I just represent this diagrammatically, what's actually going on. You start from a point, so this is going to be some x n y n, and then you're going to go in a step direction h, which you could think of as being dx, as in dx is a small change in x to the right. So then basically, this, you go up a distance dy, and you're going to follow along like this, okay? So we know dx, it's h, and we know an expression for dy by dx. So what we do dx times dy by dx. And if you think about that, well, that is dy. So we work out the vertical shift by multiplying the gradient at that point, the gradient of the tangent at that point, and we just multiply that by the small step. So dy by dx times by dx equals dy. So we just follow the tangent for a small distance, and then we get to a new point, and we calculate the gradient of a new tangent, and then we follow that, and we keep doing that until we get to the target. And the target here is y1. So basically, when we need to keep doing this until the x value is 1, and then we know that we're finished. So once we know what is y when x is 1, then we've actually we've found the approximate value for the function at x equals 1, because then we've followed the tangents to do it. So if we set up a little table, we could have xn, we could have n, so we could have xn and yn. So if we start with the initial conditions, which are x0, y0, so n is 0, we were told that y0 equals 1, so x0 is 0, y0 is 1. So that's 0 and 1. Just going to make a little table here. As far as the x goes, well, you know, we're targeting 1, and we're just going to go along by 2 each time. And it even says in the formula, xn plus 1 equals xn plus h. H is the step size, the step length, which is 0.2. So if we think about it, we actually know how many steps we need to do, because x is just going to go up by 0.2 each time, and we know we're interested in when x is 1. So we can say 0.2, 0.4, 0.6, 0.8, and 1. So once we get to there, the corresponding value of y is going to be our answer. So that's going to be 1, 2, 3, 4, 5. We need to do 5 steps. We're probably going to need a bit more room than that to do the calculations. We now need to think about how we calculate y1 from x0 and y0. We are told that yn plus 1, so the general principle is yn plus 1, so the next y equals the current y plus step length times dy by dx at that point. Dy by dx is x plus y. So our equation is the next y, yn plus 1, equals the previous y, yn, is going to start at y0, plus h, 0.2, times dy by dx, which we were told was x plus y. So it will be xn plus yn. So this is our formula. It's an iterative formula. It gives us the next value, and then we use that to calculate the one after that. So to calculate y1, well, it's going to be y0, which is 0. So to calculate y1, so when n is 1, it's going to be y when n is 0, which is 1. Let's finish this table off. So it's going to be 1 plus h 0.2 times x plus y, which will be x0 plus y0. So 0 plus 1. That's extend the table some more. Okay, so we should be able to do this one without a calculator, but I think we're going to be using it reasonably soon. So 1 plus 0.2 times 0 plus 1, or 0 plus 1 is 1. 1 times 0.2 is 0.2. And then 1 plus 0.2 is 1.2. So y1 is 1.2. Okay, on to the next one. So now for y2, we need to use the values for x1 and y1. So that is going to be, y2 is going to be y1, which was 1.2, plus 0.2 times x1 plus y1. So 0.2 plus 1.2. So even a calculation like that is probably a good idea to use the calculator. There's really no point in making a tiny error. If you're a tenth out or a factor of 10 out, it ruins everything and all the rest of the lines are going to be wrong. You're going to lose probably all of your marks, so do be careful. So 1.2 plus 0.2 times 0.2 plus 1.2. Okay, that gives us an answer of 1.48. Okay, so now we're on to y3. So that is going to be y2, 1.48, plus h, 0.2, times x2 plus y2. 0.4 plus 1.48. Go back to your calculator, 1.48 plus 0.2 times 0.4 plus 1.48. That is 1.856. Okay, so for y4, that is going to be y3, 1.856 plus h, 0.2 times x3 plus y3, 0.6 plus 1.856. Okay, so for this, I'm actually just going to use the A and S button. I probably should have done it before. I think there are ways you can build the iteration, but for so few steps, I really don't see the value in it. So I'm going to do A and S plus 0.2 times 0.6 plus A and S. And that gives me 2.3472. Okay, so the final one is going to be 2.3472 plus 0.2 times 0.8 plus 2.3472. And again, we're going to be on that A and S button for the y's, but we are going to have to change the last x value in there. So that is going to be A and S plus 0.2 times 0.8 plus A and S. And that gives us an answer of 2.9764. Okay, so we can finish the table for the last time, just kept growing and growing. And our last number is the value of y when x equals 1. So if I just remind you again, the question said find an approximate value for y1, so the value of y when x equals 1. So we'll just round it to three significant figures. So y1 is approximately equal to 2.98. Okay, so remember that this was the whole thing. It's a numerical method that follows slope fields. What you will find as your maths go, if you really go on with your maths, most differential equations are not analytically solvable. So these numerical methods, doing it like this, are often in practice in the real world the only way you can actually solve things like this. So they are incredibly valuable and relevant and useful methods to learn.